In this lesson, we will review all of the content from Chapter 10. So the first thing that we did was graph conic sections. So x squared over 9 plus y squared over 4 equals 1 is an ellipse. With a equal to 3 and b equal to 2. And that's sort of centered at the origin. So from the origin you go left and right 3, find the x-intercepts or the vertices, and up and down 2. The major axis is the x-axis and the minor axis is the y-axis. So the vertices are the points plus or minus 3, 0, and 0 plus or minus 2. And now we're going to find the foci, which are found using the formula c squared equals a squared minus b squared. So c squared is 9 minus 4, or c is plus or minus root 5, which is approximately 2.23. So we have the foci at about 2 1/4 forwards and back from the origin. So the foci are at the points plus or minus root 5, comma 0. Now in this next example, we have 4x squared minus y squared, and that changes everything, and actually is going to make this into a hyperbola. Before we graph the hyperbola, we need to make the equation equal to 1, so let's divide by 16, and that gives us x squared over 4 minus y squared over 16 equals 1. So we need to find the vertices and the asymptotes of this hyperbola. We're going to have vertices at plus or minus 2, and we go up 4, down 4 to sketch the asymptotes. We make this box, and the asymptotes always go out the corners of the box. So there's our asymptote, here's your other asymptote, and because the x squared is what is positive, you have the vertices on the x-axis, and roughly speaking, there's your hyperbola. So it has vertices plus or minus 2, 0. Had those two terms been flip-flopped, and it would have said y squared over 16 minus x squared over 4, then you would have had hyperbola in those regions. Now let's find the foci. The formula is very similar to the formula for the foci of an ellipse. Instead of minus, it's plus. We have c squared equals a squared plus b squared. So that will be 4 plus 16. So c squared equals 20, and c is equal to plus or minus root 20, which is plus or minus 2 root 5, or about equal to 4.47. So you have a focus out about 4.47, so 2, 3, 4 and a half, and there. Another type of conic section we had was a parabola, and you can tell that this is going to be a parabola because only one variable is squared. We have to convert it into a useful form first, so we're going to complete the square. So we have 6y squared minus 36y equals negative x minus 55. Take out that GCF of 6, y squared minus 6y. And we're going to add half of negative 6 squared. So half of negative 6 is negative 3. Negative 3 squared is 9, so I add 9. And since I added 9 to one side, be a little careful though, I didn't actually add 9, I actually added 6 times 9. So I actually added 54 to the left side of the equation. So I have to also add 54 to the right side of the equation. And that gives us 6 times y minus 3, the quantity squared, equals negative x minus 1, or negative 6 y minus 3 squared equals x plus 1, or x equals negative 6 y minus 3 squared minus 1. And this tells us that the vertex is at the point negative 1, negative 3, no, negative 1, positive 3. And then we know that negative 4p is equal to negative 6. This tells us the distance to our directrix and the distance to our focus, which tells us p is equal to 3 over 2, or 1.5. So from the vertex we go backwards 1.5 and we have our directrix, and forwards 1.5 and we have our focus. And we know that this parabola opens to the left because of the negative 6. And we know that it's sideways because it's x equals. Now, from that p equals 3 over 2, from the focus we can go out twice that much from that focus point. So out 3 right there, and out 3 there. And now, roughly speaking, there we have your parabola. So the focus is the point, how far back is that? It's back was negative 1, negative 2.5, so negative 5 halves, up 3. The vertex was at negative 1, 3, and since it's a parabola, we also care about the directrix. If the line x equals 1/2. So let's do another example of completing the square. This one, because it has x and y squared and both terms are positive, is probably going to be an ellipse. So first let's rearrange the terms and group the x squareds together, and then the y squareds. And now let's take out the greatest common factor, the number component of it, that is, from each group of terms. So 25 there, x squared plus 2x plus 4y squared minus 4y equals 59. Okay, now we're going to add half of 2 squared. So half of 2 is 1, 1 squared is 1, so plus 1. We've actually added 25, so add 25 to the other side. The next one, half of negative 4 is negative 2, and negative 2 squared is 4, so add 4. We've actually added 16. That gives us 25 times x plus 1 squared plus 4 times y minus 2 squared equals, so 59 plus 25 plus 16 is actually 100. Now to graph this ellipse we have to divide by that 100, and that gives us x plus 1 squared over 4 plus y minus 2 squared over 25 equals 1. So the center-ish of this ellipse is negative 1, 2. So backwards 1, up 2. And from that center we go left and right 2 because of the 4 underneath the x plus 1. We go up and down 5. That was 4. That was 4 again, so twice. Oops. we go. Okay. Now the vertices of this graph are the points 1, 2, and -3, 2. Those are the two on the minor axis. And then we also have vertices at -1, 7, and -1, -3. And let's find the foci. So c squared will be 25 minus 4, which is 21. So c is equal to plus or minus root 21. Which is about equal to 4.58. So that's 4.58 up or down from our center because of the major axis being the vertical one. So somewhere like that, somewhere like that. Now the coordinates of those foci, they will both have an x-coordinate of -1, and we went root 21 up from that center, so we'd have 2 plus root 21, and then -1, 2 minus root 21. The next thing we talked about were parameterizations of our parametric curves. So we're going to sketch the curve defined by x equals t squared plus 4t and y equals 2 minus t, for t is in between -4 and 1. So you make a table and you input t's within your domain and you plot the x's and y's that come out. So if t is -4, x is 0 and y is 6. We have this point. And if t is -3, x is -3 and y is 5. So plot the point -3, 5. So my particle has gone from there to there. If I plug in -2, I get -4 for x and 4 for y. If I plug in -1, I get -3 for x and 3 for y. If I plug in 0, I get 0 for x and 2 for y. And finally, if I plug in 1, I have 5 for x and 1 for y. And the particle travels this way. You can think about that t as representing time, and then this being the particle's path. It begins at that little dot 0, 6 on the y-axis and travels over to that other place. Now we can also get a Cartesian equation of the curve using by eliminating the parameter. In this case, it's easiest to solve the second equation for t. So we'll have y minus 2 equals -t, or t equals 2 minus y. And then we have x equals 2 minus y squared plus 4 times 2 minus y, which, if we expand it out, is 4 minus 4y plus y squared plus 8 minus 4y, or the equation x equals y squared minus 8y plus 12, which does define a sideways parabola opening to the right, so it kind of matches with what your picture is there. Now next we have a curve that has a theta as the parameter. Okay, so if you plug in theta equals 0, cosine of theta is 1, so x is 2 times 1, which is 2, And sine of theta is 0. 0 plus 1 gives us 1. So we have the point x is 2 and y is 1, right there. And then if we input, say, pi over 2, let's pick nice easy ones. Cosine of pi over 2 is 0. Sine of pi over 2 is 1, so that will be 1 plus 1, or 2. And next, let's input pi. Cosine of pi is negative 1, so we'll have negative 2. Sine of pi is 0, so we'll have negative 2 comma 1. And then 3 pi over 2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. 1 plus negative 1 is 0. So there we have the origin. And when we plug in 2 pi, well, once again get the point 2, 1 will be back there. So this looks to be an ellipse traced in the counterclockwise direction. Now here is how we prove that. Notice that x over 2 is equal to cosine of theta, and y minus 1 equals sine theta. You know, or at least you should know, that sine squared theta plus cosine squared theta equals 1. Or you know that y minus 1 squared plus x over 2 squared equals 1, which is the same thing as x squared over 4 plus y minus 1, the quantity squared, equals 1, which definitely is an ellipse. Well, the next thing we did was we did calculus with parametric curves. So we want to find the slope of the tangent line to x equals t cubed plus 6t plus 1, y is equal to 2t minus t squared at t equals 1, and then give the equation of the tangent line at this point. So recall that dy dx is equal to dy dt over dx dt. So dy dt is 3t squared plus 6. dx dt is 2 minus 2t. And so at t equals negative 1, the slope will be 3 plus 6 over 4, or 9/4. And now if we want to find an equation of the tangent line, we need to find the x and the y coordinates at that point. So at t equals negative 1, x will equal negative 1 minus 6 plus 1, or negative 6. And the y will equal negative 2 minus 1, or negative 3. And then the equation of the tangent line is y plus 3 equals 9/4 x plus 6. Given x equals t plus sine t and y equals t minus cosine t, find dy dx. So dy dx is equal to dy dt over dx dt. So that will be dy dt will be 1 plus sine t, because negative cosine t's derivative is positive sine, over 1 plus cosine of t. Now the next example asks us to find d squared y over dx squared. This is a little tricky. You've got to think about this as d over dx of dy over dx. And now this dy over dx kind of functions like that y, which means you have d over dt of dy dx divided by dx dt. You don't just differentiate the top and bottom twice. That's the most common mistake there. So d squared y over dx squared, as we just discussed, will take the derivative of the first derivative divided by dx dt. And recall that we had dy dt was equal to 1 plus sine t over 1 plus cosine t. Now to find this portion, we have to use the quotient rule, so we'll have low 1 plus cosine t multiplied by cosine t minus 1 plus sine t negative cosine t, negative sine t, excuse me, all over 1 plus cosine t quantity squared, and then divided by dx dt, which is 1 plus cosine of t. So now simplifying the numerator sum, we'll have cosine of t plus cosine squared t plus sine of t plus sine squared t all over. Now let's figure out how to deal with this. To get that out of the denominator, we'll multiply by 1 over 1 plus cosine t there and 1 over 1 plus cosine t there. So that actually ends up in the numerator. You've also probably heard that division by a fraction is the same thing as multiplying by the reciprocal. The reciprocal of 1 plus cosine t is 1 over 1 plus cosine t. So my denominator is now 1 plus cosine of t cubed. And the last thing you can do to simplify is, you know that cosine squared plus sine squared is 1. So this second derivative is cosine t plus sine t plus 1 all over 1 plus cosine of t cubed. We also found arc lengths of curves that were defined by parameters. Now the arc length formula was L equals an integral from alpha to beta, the root of dx dt squared plus dy dt squared dt. And this is also provided the curve is not traced more than one time. But this will tell you, say, like if you had a particle moving along a path, how far the particle had gone, or if you had a road, how long the road is. So we have an integral from 0 to 2. The root dx dt will be 6t, so 6t squared, plus dy dt will be 6t squared squared, so 6t squared squared dt. So 0 to 2, root 36t squared plus 36t to the 4th. And what I'm going to do there is factor out the greatest common factor of 36t squared. So 36t squared times 1 plus t squared dt. And now I can take that 36t squared out of the root sign, making it 6t, the integral from 0 to 2 root 1 plus t squared. And this integral can be solved using a u substitution. We're trying to find the value of the integral from 0 to 2 of t times the root of 1 plus t squared. So let u equal 1 plus t squared. Du is 2t dt, or half du is equal to t dt. And if t is equal to 0, u will equal 1, because you can input 0 for that t. And if t is equal to 2, u is equal to 5. So we'll have 6 over 2, the integral from 1 to 5, u to the 1/2 du. So that's 3 u to the 3/2 times 2/3, evaluated from 1 to 5, or 2 times 5 to the 3/2 minus 1. And 5 to the 3/2 is the root of 125, which is 5 root 5. In addition to the arc length, we also found surface area when we rotated curves about various axes. For this one, let's just set up the integral and not solve it. Sometimes these get really complicated, and so the one that's on your test, let's make sure it either works out very nicely or all you have to do is set it up. So the surface area formula for rotation about the x-axis is s equals 2 pi, the integral from alpha to beta, y times the root of dx dt squared plus dy dt squared dt. And here's how I'd think about it. You have this curve. It's being spun about the x-axis. The 2 pi y tells you the circumference, or how large that circle is. And then this little bit right there tells you the length of the curve. And so when you multiply those two things together, you end up getting the surface area. Okay, so in this case, x is 4 root t and y is t cubed over 3 plus 1 over 2t squared. So we'll have 2 pi integral from 1 to 4 t cubed over 3 plus 1 over 2t squared multiplied by the root. Now dx dt will equal 4 times a half times t to the negative 1/2, or 2 over root t. So when we square that, we get 4 over t. Now we need to find dy dt. So y is equal to 1/3 t cubed plus 1/2 t to the negative second. So that implies that y prime is equal to t squared minus t to the negative 3. So we'll have plus t squared minus 1 over t cubed squared dt. Now that might work out nicely. It's just going to be really icky in the process. Actually, well, let's try. So 2 pi integral 1 to 4 t cubed over 3 plus 1 over 2t squared. The root of 4 over t. We'll have plus t to the 4th of minus twice t squared times 1 over t cubed, and then plus 1 over t to the 6th. Actually, this does work out pretty nicely. Now what happens there, so we have 2 pi integral 1 to 4 t cubed over 3 plus 1 over 2t squared. Now inside this root sign, this term right there is actually just negative 2 over t. Adding it to 4 over t, we'll get t to the 4th plus 2 over t plus 1 over t to the 6th. And now that expression in the root sign actually factors into t squared plus 1 over t cubed squared. Yeek. Alright, now we can actually square root the stuff inside of that root expression. So you have 2 pi integral from 1 to 4 t cubed over 3 1 over 2t squared multiplied by t squared plus 1 over t cubed. And from there you just have to distribute and do a lot of arithmetic, but that one actually does work out pretty nicely. But in all honesty, given that your test has time constraints, you're probably just going to have to set problems up or have to make them ridiculously easy to integrate. And since this latter thing is pretty hard, probably just going to be a set it up, not solve it. So next we have polar coordinates and polar graphs. So plot the point with polar coordinates 4, 2 pi thirds, then find its Cartesian coordinates. So we have my polar axis, my origin and polar axis, 2 pi thirds will be approximately right there. And the point is a distance of 4 away from the origin. Now to convert this into Cartesian coordinates, we know that x is equal to r cosine of theta. So x will equal 4 times cosine of 2 pi thirds. And actually, I think I drew my angle a little bit off there. Probably should be up a bit higher, so probably right about there. So cosine of 2 pi thirds looks to be negative 1/2, so 4 times negative 1/2. So the x-coordinate of that point is negative 2. Now the y-coordinate is r sine of theta, so 4 times sine of 2 pi over 3, and that would equal root 3 over 2. So the y-coordinate is 2 root 3. So the Cartesian coordinates for this point are negative 2, 2 root 3. Next we have a point with Cartesian coordinates. We want to find two sets of polar coordinates for this point. So the point is negative 3, 3. So negative 3, 3. So first let's figure out what the r is. So r squared is x squared plus y squared. So in this case r squared is 9 plus 9, which is 18. So r is equal to, well, technically plus or minus 3 root 2. Now if we use positive 3 root 2, then the angle to get to that point, because of is going to be, it's 45 degrees past pi over 2, so that's 3 pi quarters. Now one other way to do that would have 3 root 2 and then go this other direction clockwise, and that would be negative 5 pi quarters. And yet another one would be to have negative 3 root 2. You would have had to have been over here to reflect there, so that would be negative pi quarters. Or you could have said 7 pi quarters. Either way, those are all correct. Sketch the region consisting of all points whose polar coordinates satisfy r is greater than or equal to 1, but less than or equal to 2, and theta is in between pi 6 and 5 pi 6. So first of all, pi 6 is somewhere over here, and 5 pi 6 is somewhere over there. And we're looking for all the points whose radii are between 1 and 2, and within that angle away from the origin. So we'll have, if this is the distance of 1, and this is the distance of 2, we get an arch, or part of a circle. Those are all the points that satisfy both of those. Next, let's sketch a bunch of polar curves. Now, I think it's easiest to first sketch the curve in Cartesian coordinates, and then use that to sketch the curve in polar coordinates. So 1 minus cosine theta, if I were to sketch that in Cartesian coordinates, if this is the theta axis and this is the r axis, negative cosine theta would start off at negative 1. By pi halves, it'd be 0. At pi, it would be at 1. By 3 pi over 2, it would be back at 0. And by 2 pi, it will be back at negative 1. So that's just r equals negative cosine of theta. 1 plus that will shift that graph up 1. So this point that was at negative 1 is now at 0. That point that was at 0 is now at 1. This point's now 2, 1, 0. And that just gives us a nice little visual way to see the r's and the thetas so that we can graph the polar curve more easily. So now when we start at an angle of 0 and actually a radius of 0, especially start at the origin. And then by pi halves, our radius has increased to 1. So once we're at pi halves, the radius has gone up so that it's 1. By an angle of pi, the radius is 2. So 1, 2. The time you get out there, you're a distance of 2 away from that origin. By 3 pi over 2, the radius has shrunk back down to 1. And by 2 pi, it's gone down to 0. So roughly speaking, there is our polar curve. Now the next one we have is 2 sine of 4 theta. And holy goodness, this one is pretty complicated. So at first we have to figure out the period of this sine function. So 4 theta equals 2 pi when theta equals pi over 2. So we go through an entire cycle of that sine function in pi over 2. So pi over 2. So it makes halfway pi over 4, and half of half eighths. Okay, then we have pi right there in the middle, 3 pi quarters. And then we'll have 5 pi quarters and 3 pi over 2, and an eighth, and then we'll have 5 pi 6, 7 pi quarters, then another eighth. 8 pi quarters will be 2 pi. Hoofda. Okay, and let's sketch this in pieces. So sine begins at 0. At the eighth, it'll be at 2, back at 0, negative 2, back up to 0. And then we'll do it again. Up to 2, down to 0, and again, up to 2, by 3 pi over 2, we're back at 0, and then up to 2, okay. So now let's sketch our polar curve. Now what I found pretty helpful was to draw in dotted lines at useful angles, like I have angles of pi eighths and pi quarters. So pi quarter would be this diagonal, and we'd also have that'd be 3 pi quarters. Now to get the eighth, you divide each of those little regions in half. So there we go. This way, this way, and then that way. So this first one is pi eighths, and then pi quarters, and then 3 pi eighths, etc. Alright, now when we start, do this color, we start at the origin, and by pi eighths we're at 2. So start at the origin, by pi eighths my radius is 2. And then as I approach pi quarters, my radius goes down to 0. Alright, next, as I approach 3 pi eighths, my radius is negative 2. So how that will plot is I will go 3 pi eighths and then reflect over. So I'll have this half. That's really hard to see. Let's make it a darker yellow. So I'll go like this, and then back up so that at pi halves I'm at 0. And then from pi halves to, that'd be 5 pi eighths, the radius becomes 2. So there's 5 pi eighths, radius becomes 2. and by 3 pi quarters back down at 0. Alright, next, from 3 pi quarters to, I guess that's 7 pi eighths, I'll have a radius of -2. So I would go over to 7 pi eighths and then reflect, something like that. And then as I approach pi, we get back to 0, like we did right there. Okay, next. Okay, between pi, this would be now 9 pi over 8. Approach a radius of 2. And by 5 pi quarters, back down to 0. So that covers this portion of the curve. The negative parts are the trickiest. Okay, now from 5 pi quarters to 11 pi eighths, I guess that is, we will have a radius of -2. So 11 pi eighths is right here, but that will reflect up to there. So we'll get that leaf this way. So that takes care of that part. And now from 3 pi over to 2, okay, that was pi eighths, 3 eighths, 5 eighths, 7 eighths, 9 eighths, 11 eighths, 13 eighths. Up to 7 pi quarters. We'll have a radius of 2, so it looks like we've got this leaf there. I think I missed one. No, we're good. Last one. And the last one is from 7 pi quarters to 2 pi, radius of -2. So that came from this angle here reflecting up into that quadrant. So there we go, there's your curve. Probably won't be that complicated on your test, but good to see a complicated example. Alright, next let's sketch r equals 3 plus cosine of theta. So once again, let's draw the Cartesian representation of the curve. So cosine of theta would start at 1, go down to -1 by pi, back up to 0, and then back up to 1. Now shifting that up 3 puts the highest point at 3 and the lowest point at, well, it was at -1, now be at, no, the highest point isn't at 3, it's at 4. Whoops. So 4, then at 3, and then at 2 is now my lowest point. Back up to 3, back up to 4. Okay, now sketching the polar curve. So we start off at an angle of 0 and a distance of 4 away. By pi over 2, we are a distance of 3 away. By pi, we're a distance of 2. By 3 pi over 2, we're back to 3. And by 2 pi, we're back there. Find a polar equation for the curve represented by the given Cartesian equation. So we know that x is equal to r cosine of theta, and y is equal to r sine of theta. So that we can translate x plus y equals 2 into r cosine theta plus r sine theta equals 2. Or we could factor out the r and say r times cosine theta plus sine theta is equal to 2, or r is equal to 2 divided by cosine of theta plus sine theta. There are lots of ways to do this, so one of many. Find a polar equation for this curve. So this is a circle of radius 8. So root 8. So r is always equal to root 8, or r is equal to 2 root 2. That's one equation. Another equation could be r equaled negative 2 root 2. Let's find the slope of the tangent line to the graph of r equals e to the negative theta at the point theta equals pi. So what's easiest to do here is recall that x is equal to r cosine of theta, and y is equal to r sine theta. And r is that function you have up there. And remember the differentiation for parametric curves. We had dy dx would equal dy d theta over dx d theta. And so using this r and that y for the x and y, what we will get using the product rule, so dy will be dr d theta sine theta plus r cosine of theta over dr d theta cosine theta minus r sine theta. It's probably easier to remember how to derive that than to memorize the formula itself. And now let's just plug everything in. So dr d theta will be negative e to the negative theta sine theta plus e to the negative theta cosine theta over negative e to the negative theta cosine theta minus e to the negative theta sine theta. Now we can factor out and cancel an e to the negative theta times negative sine theta plus cosine of theta, all divided by e to the negative theta, negative cosine theta minus sine theta. So those e to the negative thetas can cancel. And we can find the slope of the tangent line by plugging in pi. So at theta equals pi, the slope of the tangent line, so sine of pi is 0, so we'll have negative 0. Cosine of pi is negative 1, divided by cosine of pi is negative 1, so positive 1 minus 0. So in the end we have negative 1 divided by positive 1, which gives us negative 1. So find the area enclosed by the curve r squared equals 9 sine of 5 theta. Now this one is a little bit tricky, so if I gave it to you, I probably would give you a picture and I would give you bounds. But one loop of this curve is transversed between 0 and pi over 5. So I will have to tell you that because thus far I haven't found a textbook that really explains to me exactly when and how you can figure this out. So bear with me. So the area formula for a sector was 1/2 the integral from A to B, or a polar curve that is, r squared d theta. So for one loop, and there are 5 total, like I said, I would show you a picture. You could graph it using multiple, online graph or something like that. We'll have 1/2 the integral from 0 to pi over 5, 9 sine 5 theta d theta. So that's 9/2. The antiderivative of sine is cosine negative 5 theta over 5, evaluated from 0 to pi fifths. So that will be 9 over 10 times negative cosine of pi plus cosine of 0. And cosine of pi is negative 1. Cosine of 0 is 1. Together those add to, double negative makes positive, adds to 2. So I have 9/10 times 2, which is 9/5. So for one loop, so the total A is 9/5 times 5, or 9. Find the points of intersection for the curves r equals 2 and r equals 4 cosine of theta. So you can set the curves equal to one another, but it is possible to miss points that way. So let's graph them. Let's first do the solving, then we'll graph them to verify that we actually caught all the points. So 2 equals 4 cosine of theta. So a half equals cosine of theta. And that occurs when theta is equal to pi thirds and 5 pi thirds. And let's just see if there are any more. So r equals 2 is pretty easy to graph. That's a circle centered at the origin, radius 2. Now 4 cosine theta isn't super hard. Let's just pick some thetas, find some r's. So if theta is 0, r is 4. If theta is pi over 2, r is 0. And if theta is pi, we're at -4, so that would take this point, reflect it back onto that one. So it looks like we also have something sort of circular, and those have only 2 points of intersection. One appears to be up here, and that would probably be where theta is pi thirds, and one down there where theta is 5 pi thirds. But that isn't always going to happen, so we're going to make sure, what we'll probably have to do is make that question 2 parts in a test, and I'll say graph and then find the points of intersection. So set up, but do not solve, an integral that will find the area of the region inside of r equals 2 sine theta and r equals sine theta plus cosine theta. So first let's graph 2 sine theta. So if theta is 0, r is 0. If theta is pi over 2, r is 2. And by pi, we're back at 0, and then we're just going to cycle. So this will actually be a circle. You can prove that that's a circle. Now let's graph the other one. So we'll have theta r. So first, if theta is 0, sine of 0 is 0, cosine of 0 is 1. So we're right there. If theta is pi over 2, once again, the r is 1. So we go here. Now when theta is pi, the radius is -1. So that's going to take this point and reflect it back onto that point. So we're actually going to have something sort of like this. So we're going to find the area that is inside or in between these two curves. So what you have to do is find that point of intersection first. So 2 sine of theta equals sine theta plus cosine of theta. So sine theta equals cosine theta. That happens at, well, the one that we're seeing is pi quarters. So we're going to call this little region A and this little region B. So now the region of A that we care about is actually, which you can tell that when that radius is back at 0, is actually at the angle 3 pi quarters. Because at that angle the sine and cosine are opposite, so they add to 0. So this part of A's curve is swept as theta varies from pi over 4 to 3 pi over 4. And remember, the formula for area was 1/2 r squared, so that'd be 1/2 sine theta plus cosine of theta squared d theta. That whole thing will find area A. if you work it out, which takes a little bit of work, and I did it on the notes if you want to look online, that gives you pi quarters. Now area B, so we'll have 1/2 we have to figure out, that is swept as we go from 0 to pi quarters. And there my r is 2 sine of theta squared d theta. So those two integrals, and when you work that out, you end up getting pi over 4 minus 1/2. So your total area is A plus B, which will work out to be pi over 2 minus 1/2. So it probably won't get that tricky, but the areas in this system are a little bit complicated. And the last thing we did with polar curves was find the arc length of them. So the arc length formula for this simplified down to an integral from A to B root r squared plus dr d theta squared d theta. So now in this case, dr d theta will equal 3 sine squared of theta over 3 multiplied by cosine of theta over 3 and then times 1/3, or it will be sine squared theta over 3 cos theta over 3. Okay, so our length is given by an integral from 0 to pi. R squared will be actually sine to the 6th theta over 3 plus sine to the 4th theta over 3 times cosine squared theta over 3 d theta. Now I'm going to factor out a sine to the 4th and then square root it. So that will give me 0 to pi sine squared theta over 3. And because I factored out a sine to the 4th, I have sine squared theta over 3 left behind, plus cosine squared theta over 3. And look at that loveliness. That's just equal to, or the root at least, is equal to 1. So I now have the integral from 0 to pi sine squared theta over 3 d theta. And now to find this integral, you have to recall that sine squared of theta is 1/2 1 minus cosine 2 theta. So we use theta equals pi over 3 there. So 0 to pi 1/2 1 minus cosine of 2 theta over 3 d theta. So that will be 1/2 theta. The antiderivative of cosine is sine, so 3/2 sine 2 theta over 3, evaluated from 0 to pi, which when you work it all out, details are online, you get pi over 2 minus root 3 over 8. Pretty sure.